Okay, the slide is here. Okay, as I said, I'll release your last assignment till next Monday. Okay, early next Monday, and then yeah, make sure you submit by Friday midnight. Okay, the assignment one. The goal for today, I will go over some new concepts over here, and then for certain parts, they do have some algorithm, but I will trace them possibly on Monday. Just get some big picture first. Okay, it's a very interesting idea actually. The goal will be we want to improve the performance for the top-down parser that we have been talking about. Okay, let me first of all get to the slides quickly. And what we talked about last time, we talked about direct versus indirect left recursions, and we want to know how to remove them. So what I promised to do, I will at least do a few in details together with you, because I will expect you to follow the same procedure later to remove the left recursion. Okay. So what I would like to do is go over this algorithm, not just the abstract version, but I'll run it through and then try to see how we can discuss that. Okay. Let's just try some examples here. This one not here. Sorry. Let's see. We want to remove left recursion for this one here. Okay. And as soon as you see the grammar over here, you can see that immediately tell. Does this grammar have any indirect left recursion? First of all, indirect. As far as you can see. Actually, not really. I can tell you no. However, it's quite obvious we got direct left recursion, right? Because you can see expression appears right after expression. Okay. So let's run it through this quickly. Okay. To really see the algorithm. There was something I could have made a little bit clearer on Monday, but I didn't. But I'll try to make it clear this time. This is how you can think of the algorithm. First of all, the first line is really important. You want to impose some order on the variables. I would say just follow the order in which they appear on the grammar. I would say this expression is simply 1. Term will be 2, and factor will be 3. Okay? And then, as I said, the first stage over here, for this, we are actually going to remove the indirect recursion. Indirect left recursion, indirect. How do we do that? So we got I and we got j. Okay, so the pattern goes like this. So let I and j. Okay, so now when I is equal to 1, j will be only up to I minus 1. So that one is not applicable. Okay, 2, 1. Okay, and also 3, 1 and 3, 2. First of all, let's understand these are the iterations we're going to have to run, especially these 3. Let's see exactly how you're supposed to interpret the algorithm. So now I want you to have a look at this particular line here. We want to tell to see if there's a possibility of left recursion indirectly. So we want to prevent it by removing that right away. Okay. So now how do we read this? This one here is AI produces AJ. So now let's say for this particular iteration over here, what's AI? A2. A2 will be term. Produces, and then A1, right? So J will be 1. 1 will be expression. Is there such a rule in our grammar? Is there anything which will say term produces expression and then something? No. Okay. So that means for this particular iteration, this over here will just be false. Because there's no such rule. That's something I didn't make clear last time. Okay? Can I just repeat once more? Just make sure you're okay. The way we do to remove the indirect left recursion systematically is by, first of all, having order of the rules, 1, 2, and 3, for example. And then for each iteration, we have to say, given the indices of I and j, we have to see if such a production exists. For example, when this particular iteration where I is equal to 2 and j is equal to 1, we want to find out if there is any variable number 2 that produces variable number 1. Variable number 2 in our case is term. And then variable number 1 is actually expression. Do we have term producing expression? We don't. So in this case, it will just be false, in which case we just don't do any replacement. Okay, that's the first one. Any questions? Okay. Now, when we go to the next iteration, I is going to be 3 and j is going to be 1. So which are we looking for, basically? 3 will be factor, produces, 1 will be expression, right? You can see factor is 3, expression is 1. Do we have anything like a factor produces expression? Be careful, why not? Exactly. So you might be thinking about this guy here, right? But remember, this is brackets. It has to be the first one. Okay, so no. Okay. So far so good? Okay. And also false. Let's do the third one. So now if I got 3 and 2, so that means I'm looking for 3, which is factor, produces, and also 2, turn. Do I have anything that's factor produces turn? I don't, right? Okay, in that case, that will also be false. So that means for all the 3 iterations, I will all get false for this particular condition. So that means this part here is not executed at all, because there's simply no indirect left recursion, okay, for this particular grammar. Any question about this? Yes? You know what? The indentation should be fixed a bit, I just noticed. Sorry about that. I should be more careful. So this guy over here should be, I think this guy here, I and I, okay. This guy here should be a little bit to the left. It should be a second stage. Yeah, I should be more careful. Oh, wait. I think this is I here. Oh, actually, sorry. That's actually fine. Sorry about that. Basically, we're saying that for any particular value of I, the first thing you do is to remove all the possible indirect recursion by finding all the lower indices than I. And then the second step is to remove any direct recursion specific to AI. Let's see what's going to happen, okay? So now I'm just handling basically just the this part over here, just this part. Okay, just this part here. Okay, so now let's say we go to for this particular guy here. Okay, so now I could be basically 1 or 2 or 3, right? In this case, right? When I is equal to 1, do I have A1 produces A1? 1 is basically expression. I do have expression produces expression. First of all, let's realize we do have direct recursion, right? And also similarly, we got turn also produces turn. But for factor, we don't. So it's false. Okay? So these are the 2 direct left recursion we have to remove. But how do we do that? Okay? Let me do this more carefully in fresh slides and then show it to you. Okay, 1 here, and then let me get a clean version in another one. Okay, assuming that we already finished executing this particular part, okay? So this part is already done, okay? This part is done already, let's say. So now when I was equal to 1, when I is equal to 1, so that means we do have expression produces expression. So this particular guy is a direct left recursion. So how do we remove it? Okay, let's look at the pattern here. Okay, it tells you if you got AI produces AI followed by any alpha, you can see this particular part is alpha. Okay, or any other alternative, in this case beta. And Abdul, you asked me last time, is this beta a single one or can be alternative? It could be alternative. It could be beta 1, beta 2, beta 3, etc. Right? In which case you got to handle all of them. But in this case, just 1. So now this guy here is beta. Okay? So now how do I remove it? I simply follow some standard procedure. So what I would do is, first of all, replace it with, so which means the pink one over here is now going to be replaced by, so first of all, AI, which is expression. Produces should be beta, which is turn. And then you got to create some new variable. I would say usually just prime, the original one. Expression, prime. Okay, and then followed by expression, prime. The new variable produces. So now alpha is basically this guy here. So be careful, okay? So that's why you saw plus turn. And then followed by expression prime. And don't forget, you may just have no, just one single term. So that's why epsilon should be here. Okay, that's one instance of removing the direct left recursion. Everybody okay with this? Okay, and now it would be an exercise for you to remove the direct left recursion for this guy here. Okay, so for this guy here, exercise for you. Okay, any question about this process so far? For this particular grammar, we only had to do some useful stuff in the second stage because we got direct left recursion. On the other hand, for all these kind of steps to remove the potential indirect, we didn't have to do anything because there's no such possibility. Okay. Yes?
So I think the second stage should actually be outside of the...
No, actually, you know what? I realized that the way I trace it, let me make it clear. The algorithm is actually right, okay? So what I should have done was like this, okay? Let me make it clear. Just the order of tracing, okay? Let me make it clear to you, okay? Let's say this.
I know, because if you are doing the second loop inside that loop, by removing one rule, you are adding two rules. So you're messing up with the index of the rules. So basically,
Yeah, so I would say, abstractly speaking, so I would say you have to keep track of what you're doing over here. So we are not really talking about any implementation issue here. So aliasing or whatever, that's not the issue here. Just think about what you're going to do to remove one after another. Mm-hmm. Maybe you'll be clearer if I move this guy here as a second stage separate from this particular loop. That may be another implementation. But I'll just kind of follow what the textbook says. Yeah. Okay. Anyway. Okay, guys, any question, confusion here? Okay. If everybody's okay, I would suggest this guy here will be very similar in the sense that you will see that there is no indirect left recursion. Okay? If you try to run this particular example over here, you'll find that for this particular stage, you didn't have to do anything. Okay, similar to the previous one. However, for the direct left recursion, you will have to do something, like what we did. For example, expression here, turn, and also turn here, expression here, right? So this example here will be very similar to how we did it for the previous one. Okay, I'll leave it to you. Okay. Okay, so that will be exercise for you. Any question, please? You can think about it as an independent example. I'll just give you a different grammar. Yeah, just different grammar. Over here, you don't have to worry about how factor is defined. I'll just give you a partial one. Okay. Okay, I'll let you do one more together with you. Since so far the two grammars we're considering, we didn't have to do anything to remove the indirect left recursion. Let's do one example where we do have to remove them. Okay, let's see. So now for this guy here, so let's see how we can do it. Okay. Let's say, well, this one's pretty easy. I'll do this one together, and then I got another one, slightly more complicated. I'll leave that to you. Okay? But similar idea. Okay? So now, how do we do for this one here? Would you agree there's no direct left recursion? Right? Very good. Okay? So now, let's have a look. Let's say we try to run this particular pattern here. So let's say 1, 2, and 3. Again, we got I and J. Okay. When it's 1, now packable, 2, 1, 3, 1, and 3, 1, oh, sorry, 3, 2. Okay, so again, the 4 combinations here we got to worry about, okay? Let's say this. When it is 2, 1, what's going to happen? When it is 2, 1, so again, we are considering this particular condition here in the middle, okay? Just, again, you got to read it through to make sure you really understand that one there. But now, we are basically saying, is there any A2? Is there any A2 produces A1? Which means, do we have anything that's B produces A? Do we have it? We don't, okay? So that is, for this one here, it's going to be false. So we don't do anything just yet, okay? We're doing this systematically, so you got to bear with the loop running. Okay, let's say the next one, when it's 3, 1. So now that means we got A3 produces A1. A3 will be C produces A. We do have it, right? So now that means this guy over here somehow has to be replaced by something, okay? The way we replace it is by saying this. AI, the same, so C produces something. So now this should be all the alternative that can actually happen to the variable you're referring to. In this case, A. A can be just BR, right? So we're going to replace A over here by BR. BR and then T. Is it okay for this one? For those of you who might be lost, you may just want to read the algorithm again and try to see if you can trace it. That's quite important, okay? Okay, so now after this particular guy, we got BRT, okay? So now it's already changed, okay? So now what we should do, the next one, is to see 3 and 2. Okay, let me see, A will be replaced by BRT. And now, if I try the next one, 3, 2 over here, so now I'm basically saying, do I have anything that's from 3 to 2? Yes. Do I have A3 produces A2, which will be C produces B? Do I have it? Yes. I do, yes. So now, basically, C produces B. Okay? So that means, Chelsea, just let me finish that, and then I'll take a question. Okay. So now you can see that over here, you want to replace, thinking this way, this is AI, AI is C, and AJ over here is B. Okay? And gamma here is RT. Okay? And now you want to see exactly how C can, over here, you want to see AJ. AJ here is B, and B here can map to CD, right? So the only delta 1 you have over here is simply CD. That's why you got to replace. Yeah, let me finish that, and I'll definitely take question. So now that means you can now replace this by C produces, so B will be replaced by CDRT. Okay, so that should be the final answer over here. Yes, I'll take question.
So then, can we have
I agree with you, yes.
the next stage and
Exactly, exactly. So now, Chelsea made a very valid observation. It is quite expected when you are finishing this particular for loop, let's say for when I is equal to 3, right? As soon as you're done with it, you can see the next one is to deal with a direct left recursion. Okay, so actually go back to your question. So the indentation is actually correct. Okay, so now from the first stage, you might expect direct left recursion resulted. In that case, you have to use this particular procedure to remove the direct left recursion. Okay, why don't we do that quickly, and then I will take a question. How do we remove the direct left recursion? Anybody want to try? Go ahead, let's go. C produces, first of all, let me just make some substitution for you, okay? Apparently AI over here is C, okay? And then alpha over here is DRT. DRT, and beta we don't have anything. You can think about just more like an epsilon. Just actually you shouldn't think epsilon, just nothing, just not there. Okay, and then so what you will do is C is going to basically C prime. Yeah, because beta over here you can think about it's just nothing. Okay, I'll just put epsilon. Okay, and then for here we just say C prime will be DRT. Okay, so this part is DRT, and then I would say C prime or epsilon. Okay, it's quite a standard procedure you gotta apply, right? Mm-hmm. Okay, I'll take questions in case you got some confusion. Raymond first. Yeah.
In that highlighted line, like let's say B maps to more than C or D, do we just get to pick?
You mean for the yellow line, line number 10?
Yeah.
I would say for line number 10 here, think about we're just executing the algorithm, faithfully. So when you are executing this algorithm, you don't have a choice. all you got to see is for this current iteration, for example, if I'm talking about 2, 1, for example, so that means when I'm trying to evaluate this particular condition over here, I'm only checking to see A, in this case, I would be just 2, produces an AJ, which would be 1. Does A2 produces AJ actually exist?
I'm at line 11.
Line number 11, yes?
Like, you know how we say that B maps to C, D?
Mm-hmm.
What if B maps to more than one thing?
B maps to CD. In that,
Something else.
in that case, you got to replace for each one of them.
Oh, for each one.
For each one of them. I'll try to maybe prepare another example for you to maybe go over another one quickly. But I'll say just deal with simple case first. But that simply means you got to deal with each occasion, each iteration, just one at a time. Yes?
So, since you said that C gets replaced with C and
BRT. Oh, you mean here, eventually, right?
yeah, do we have to like reiterate on the new C and C prime?
You don't have to. You don't have to. You just go with the old indices, just C. Yeah. Mm-hmm. Yeah, could be. Yeah, that's more like an implementation issue. So Abdul's concern was, since we are creating this particular, since we are creating this particular new variable C prime, do we have to include it in this particular pattern? You don't have to. You don't need to, right? Okay, think about this, right? I think this one here, we got to just go step by step. That's why it can be a little bit easy to lose. But you got to think about it in more isolation. Yes.
I don't know if this was specific to this grammar.
Yeah.
But does this algorithm, in a general sense, I don't have tracing this exactly, convert indirect left recursions to left recursions? Sorry, convert indirect left recursions to direct ones, and then remove the direct recursion?
I would say, yeah, so I would say it's not always the case. Not always the case. So Chelsea's concern was, is it always the case, given some grammar, after the first stage, it always generates left recursion, direct left recursion? Not necessarily. If it does, you don't have to worry because the second stage will just remove them. Yeah, okay. Let's say if there's a grammar where there's simply no indirect nor direct left recursion in the grammar. In that case, you don't have to do anything. The grammar will just be the same, right? Okay, good. So there's another one here. Give a try. Okay. So not now. Okay, try that maybe over the weekend. Okay, we just gotta move on. Okay. Give it a try, and then if you really got concerned, speak to me. Okay. Yeah. Hopefully that's enough just for getting you interested for the algorithm. So now, one interesting question to think about, right? Given that we have got some feel about the algorithm, okay, here's my question. Take a look at, let me just give you a little bit context over here. We want to come up with the looping variance. Well, just get some idea, and then I'll give you the answer. If you think about for each value of I, we have to do stage number 1 and stage number 2. Stage number 1 is going to remove the indirect recursion, right? And for stage number 2, it's going to remove the direct recursion, as we said, 2. Now, if I want to insert right over here at the start of the loop over here, right before I perform the 2 stages for this particular I value in each iteration, I want to assert certain looping variance over here to say this particular condition should be true for every start of the loop. What should it be? I'll give you a little bit hints. If the current value is I, what am I, if the current value is I is 1, okay? Before I take Misgov's answer, I'll give you a little bit hints to think about. If currently I is simply just 1, let me just make it 3, just make it a little bit easier. Make it 3, okay? If I have the current value of I being 3, so that means after the 2 stages, what's going to happen? Does that mean I'm going to do something to all the variable with lower indices? Isn't that what I'm going to do? That's kind of what a looping variable will look like. Okay? Anybody? You're saying index lower than I? does not have any recursion. That's basically right. You're saying that if I'm currently at I value, any variable with indices strictly smaller than I is guaranteed. They don't have any indirect or direct left recursion. That's basically a looping variance. Okay, that's something for you to think about. And if you look at the slides, at the start of the ith iteration, right? So that means I minus 1, the previous iteration, have done something already for us, right? So now you will simply say, no direct or indirect left recursion from A1, A2 up to I minus 1. That's from the previous iterations, right? Of course, when I is simply equal to 1, this particular list will just be empty, so nothing to assert, which is like a for all false range. That will just be true. Okay, that's the more precise practical logic, but I'll let you read it. Okay. The looping variant here is very, very interesting. That just help you, maybe after you have traced the code by several examples, you can actually see what's going on at the start of each iteration. Okay, think about it. Okay. Any questions about this? Okay. All right. Now we talk about how you can eliminate our epsilon productions already. So let's move on. Okay, that one I'm gonna just skip. Okay, we already did it. So now we want to talk about backtrack-free parsing. I remember Mahu was sitting here on Monday and asking me. Actually, he was making a very nice observation. Basically, when you try to, if I can bring back the diagram, so that'll be easier, just to refresh your memory. Okay, I think this guy will be good. So this is one of the tracing we did on Monday. Okay, so now the main bottleneck for performance at the runtime is, let's say we have built our tree up to this over here, but somehow maybe the current symbol does not quite match the word, which means we have to backtrack to the previous one and then somehow prune off the tree we have built so far. That's a backtrack process, right? At the runtime, it's no guarantee how deep the backtrack should go. It could be that you have to go all the way to this deep for your particular subtree, but now you find that you should backtrack all the way back to the start symbol and then start building the tree over again. So that's very inefficient. So that means it would be very nice if we can modify. I'll show you exactly a line of code you may want to modify, and then we'll see how we can do it. Okay, that's the interesting part about the top-down parsing, the second part. Okay, so now let's look at this algorithm here. Okay, it's the same as before. I am going to tell you exactly which line you may want to consider changing. Look at this line here, the blue one, right? That one is really the key when we trace a top-down parsing, which means if the current focus is actually a variable, that means we want to consider growing this particular internal node. For example, let's say if currently the focus is actually, for example, let's say let me find a good example. Let's say turn. Okay, if currently we are now somewhere in the tree, we are now in turn. Okay. Turn prime maybe. Yeah, turn prime. Okay. So this is the node that we have right now. Let me write it better. Now, in order for me to grow this particular subtree, how many choices do I have? I can either go for this one, I can go for this one, I can also go for epsilon, either one of them, right? I got 3 choices. According to the algorithm, I'll simply choose whatever that has not been visited so far. In that case, I might just choose the first one because it's simply unvisited, but it might be the wrong choice. Okay? So now, what we want to do is to say, add a conjunction over here, add a condition over here. To say when you are making such decision, of course the rule has to be unvisited, but more importantly, you have to somehow consider if the current word is, for example, let's say multiply, for example. If the current word I want to match will be multiply, and then would it be obvious to you which rule you should really choose, for example? Should be the first one. But what if, let's say, the current one is simply just divide? And I should not choose the first one, right? I should really choose the second one. So I actually allow the parser to somehow look ahead to see what would be the consequence if I apply each one of the rule. To say, if I apply this particular rule, the first symbol is going to be simply just multiply. If I apply this particular rule, it's going to be divide. If I apply that, it's going to be epsilon. So now, which one of them matches the current word I want to match? The second one. So I should choose the second one rather than the first one. That's more like a look ahead process we want to learn.
How much does this save like a
This, I would say on average, basically. Well, you know, I tell you what, if we implement this properly with a look ahead, you don't need any backtrack anymore. There's not simply no possibility of backtrack. Save quite a bit. A lot, yes. When I say quite a bit, I mean a lot. Mm-hmm. Yes, Chelsea.
Are we looking at one token or multiple tokens?
One token. Just look at one token. Yeah. Yeah, so the idea would be, okay, so what we're going to see now is, I don't want to give you a little bit intuition about where to change and then how you might change it. Let me just draw a little bit cleaner picture here. Okay, let's say this. If I'm trying to deal with this particular term, okay, and I know that I got choice number 1, choice number 2, and choice number 3. I'm going to introduce something called the first. It's going to be a set, okay? What I would do is, I'm going to systematically compute what's going to be the consequence if I apply the factor term prime. And what's going to be the consequence? Oh, sorry, I highlighted the wrong thing. Beg your pardon. Let me do it again. It should be here. Multiply, divide, and epsilon. We got 3 possibilities over here, right, for term prime. So I'm basically asking the following question. If I apply this particular rule, what's going to be the first symbol that will appear in the derivation? In this case, it's obvious. It will simply just be multiplication. Okay? If I apply the second rule over here, it will be division. If I apply this third one, it seems to be just epsilon. That one's a little bit tricky case to consider later. Okay? But now, which one of them will actually match star? In this case, just the first one. So I can just choose the first one. Okay? But we should know how to calculate this particular first set. That's the issue over here. So we're going to see. Okay? There is algorithm for calculating the first set, but I would suggest we go over some examples first before we try to trace the algorithm. We'll trace the algorithm on Monday, maybe. Okay? Let's just go over some slides. Okay? Just to talk about the idea. Okay? Let me just go through some reminder about top-down parsing. So that one's going to automate top-down leftmost derivation process, as we said. And then we have to choose production rule consistently. But the way we did it previously is just by in the order that the rules appear in the CFG, right? But that one definitely requires backtracking in the worst case. You might have to backtrack all the way to the star symbol. It's very inflexible and also inefficient when you need backtracking. Okay, it's something I explained already. And this is the worst case. You might find that you're now very deep down to the tree. But now you find that your very initial choice about the production rule from the star symbol was simply just wrong. So you got to backtrack all the way to the root. And you got to prune all the tree. And start from scratch. That's very inefficient. It would be very nice if we just made the right choice every time. It would be very nice. Okay, so now we may avoid backtracking with some modification. I just mentioned just that particular predicate. We have to check some additional condition. Okay. So now when we decide which production rule to choose, we had to consider several things. Okay, let's see what we had to consider. The focus symbol, for sure, still. That's the same as before. But now, we want to see what's the next input symbol, or the next symbol that can be derived from the production rule we chose. Okay, that's basically the 2 things we want to consider. And it's called look ahead symbol. Okay, usually it's just look ahead. Right? You want to look ahead to see if I apply this particular production rule, what will be the consequence for the resulting string. Okay, and now if you're using a one symbol look ahead, you can really try to really find a unique terminal that will be matched, and then to see which one to choose. Okay, so you can avoid backtracking. So later on, we're going to define. When you got a context-free grammar, you would say that particular context-free grammar will be backtrack-free. So this will be the ideal grammar you want to use for your top-down parsing because, number one, you don't have any infinite loop. And number two, you can always make the right choice about choosing the production rule. Okay. Okay. We also call that predictive grammar. Okay. Just some term from the textbook. Any question about this style in general? Yes.
So if you have say the symbol you're looking for is in the last production rule, and that symbol itself is in the rightmost branch.
No, actually, no. You will actually see that this approach is very general. Okay. If I may try to do a little bit of stuff over here. Let's say this. Let's say currently I'm trying to do the variable a, okay, somewhere in the parse tree, right? Let's say that's a root. Let's say the root, maybe very high, okay? Let's say according to my grammar, I got a produces maybe alternative number 1, number 2, number 3, and number 4. I got 4 different possibilities, right? So now the idea would be also at the same time, of course, now the focus would just be A. Okay? And now I want to know which rule I should really use in order to expand the subtree for A. That's what I want to know, right? The idea about the lookahead is as follows. Let me just repeat it quickly. We also got the current word that I want to match, some symbol over here, right? Some concrete symbol I want to match. That's from the input token. And now I want to know what's the consequence of applying this rule. What will be the first symbol? That's something we'll see. I'll give you a concrete example. And then we want to see the first set for this, for that, for that, and for that. Basically, intuitively, think about what's the first symbol that's going to appear for each rule. That's not exactly precise, but they're just approximation for now. Okay? Once you compare this 4 symbols against this particular word, it's guaranteed just one single one that will actually match. If it doesn't match, it's not backtrack free.
And if two can match, it means that grammar is not.
It's not, no, nothing about ambiguity. So let's say if you got exactly one first symbol that matches the word. If that's true for every production rule, right? That means your grammar is backtrack free. Okay? That's one thing, okay? Now, if for some reason your grammar is such that maybe these two, more than one, let's say more than one first symbol match the word. Does this mean my grammar is ambiguous? No, don't get it wrong. Okay? That simply means the grammar is not backtrack free. Which means if you use that particular grammar, you might just need some backtrack. It doesn't really mean you cannot find a unique parse tree. Okay, just get it clear. Okay. Okay, I have another question for you. Okay. If let's say a specific case, let's say this is my star symbol. Okay. And my star symbol basically produces 1, 2, 3, 4. Okay. Let's say I have a condition for you. Let's say this is rule number 1, rule number 2, rule number 3, and rule number 4. What if the first of rule number 1, rule number 2, rule number 3, and rule number 4, all of them all mismatch the word? So what does that mean? Let's talk about this special case over here. let's say I'm currently trying to expand the internal node that represents the star symbol. And the star symbol actually produces 4 possible rules, R1, R2, R3, and R4. And somehow I figure out the first symbols for rule number 1, rule number 2, rule number 3, and rule number 4. But none of them matches the word, the current word. None of them. So what does that mean? What should we do? How about this? In this particular special case, we're now already in the root of the parse tree, and then it seems like none of the first words of the production rule actually matches the word I'm looking for. In that case, what does that mean? Does that mean there's something wrong with the grammar, or there's something wrong with the input, or what else? That's the question. Andres.
We're assuming that the first character.
Yeah, you can think about intuitively, it's more like a first character that will actually appear.
It's not another variable.
It's not another variable, it's just a constant. Yeah, just like a symbol, like a token. Yeah. Yes?
Can it be indirect?
Indirect, you mean about recursion? Nothing to do with that.
No. So
Mhm.
for example, we have a bunch of variables.
Mhm.
The very last one will produce what you.
No, we remember the way you actually match the string is to make sure each production rule is going to give you that particular part of the string, right? But now the problem is, all the rule that's available over here, their first symbol already mismatch the word you're looking for.
So I'm just assuming that it's backtrack.
Well, you say backtrack, but we are now, I'm saying we are now in the star symbol already, right? How do we backtrack from the root?
Just
Hmm?
you don't have like.
Oh, yeah, behind. Yeah.
I'm guessing that just means the input is wrong. You can't go.
Exactly. That's what I wanted to hear. Exactly.
You can't go anywhere else.
Exactly. So you keep backtracking until you are now in the star symbol. If you still want to backtrack, that means you have nowhere to go. The input is simply just wrong. Okay? So this one here is simply, that means the input is invalid. Has syntax error. Okay? Just to mention that. But so far we haven't talked about exactly how the first symbol looks like. I want to give you some intuition first. Okay? All right, so that's the slide. So now let's talk about the first set. Okay? I will talk about definition first and then we'll do examples. Okay, once you see the example, it's not too bad. I'll do the algorithm tracing maybe on Monday, okay, together with another set. We'll see how much we can do. Okay. For definition let's say we're going to use T to represent all the tokens, right? You can think about T is going to be just a sequence of alphabets or characters, right? For example, while loop, the while, or the if, then, or else, okay? Just tokens. So now, here's the first set. So now, the first set over here is going to be just a set. Later on, maybe in a quiz, maybe the exam, I'll give you the grammar, and then I would say, compute the first set of maybe this particular terminal. We'll compute the first set for this particular variable. Okay, that will be the kind of the question. But we'll do examples. So now the alpha over here can be either a variable or it can be a terminal. Okay, either way. So now it's going to be the set of symbols that can appear as the first word in some string deriving from alpha. Okay? So now, before I show you the formal definition, why don't we take a look at some example? Can you just look at this informal definition here for me? Okay, read it through, and then keep that in mind, and then we'll do examples to build your intuition. And then before we see the math. The result from the first is going to be just a set of symbols. The set could be singleton, just a single character, or it could be many characters, or maybe many words. That's what I meant. And then that can appear as the first word in some string derived from alpha. If alpha happens to be a variable, that's why we can derive some string from variable, right? Okay, let's take a look. Okay, for now, you can, for temporarily, you can ignore this particular part. Okay, don't worry about it for now. Okay. I want you to look at this particular grammar. It's right recursive. Okay. So take a look here. is go produces expression produces turn, followed by expression prime, and etc. Okay, that was right recursive, no left recursion. Okay, so it's safe to use it for top-down parsing. Okay, so now we want to calculate the first. Okay, whenever you want to calculate the first, you can do it in two categories. The first category will be the terminals. That might be easier for you to do, and also you do for variables. Okay. And let's try the first one. The first one here, I simply say num. Num simply means over here maybe 1 or 2 or 3, you know, just literal. Okay? What would be the, for example, let's say in the case of 1, what would be the first symbol you can derive from 1? Just 1. Yeah, basically terminals are the base cases for first, if that makes sense to you. Which means from any number, the first will just be the number itself. Any variable name, for example, if you have some program variable name, let's say Alan, for example, right? Just some variable name. In that case, it will just be Alan, so the name itself. And then it should make sense to you. Plus will be plus, minus will be minus, and then multiply, divide, etc. And the file, and also absolute. This table is very trivial, but it's the base case we need. Okay. Any questions? The more interesting bit is to see how we can build up the first set for expression. So now for the variables, I would like to remind you once more, okay? So that will help you. So now let's talk about variable case. For the moment, assume alpha over here is simply just a variable. We are figuring out the set of symbols that can appear as a first word in a string that can be derived from this particular variable, according to the grammar, right? So now let's take a look. Let's take a look at expression. Okay. According to the grammar, we have expression starting from here. So what would be the first symbol? Don't tell me it's turn. Turn is not a symbol. Open bracket, how did you figure?
Because you go to term, and then term goes factor, and then factor.
Yeah. I'm just very good. Okay. So now we're just trying to do this example informally and manually. You will see on Monday some algorithms doing this. I'll go through that on Monday. Okay? Exactly right. Expression must start with turn, first of all. And notice that turn itself cannot be turned into epsilon. Okay? So that actually simplified the matter a little bit. Okay? And turn over here can also first go to factor. Keep going for the first one, basically, right? And then factor can now go to the first symbol will be parenthesis, and then what can be none, what can be name. So that's exactly the first set for expression. Exactly. Good. Guys, any question about the first set for expression? I can give you a little bit preview. It will turn out calculating the first set is not enough. We have to calculate another thing called follow. Interestingly. But anyway, let's do first. I just want to give you a little bit heads up. Okay? How about we do the second one? How about expression prime? Okay, let me just use a different color, and then how about this? Green. Green has been used. How about blue? Expression prime. Anybody? What should be the first for expression prime? Yes. Oh yeah, it's a plus. Yes. Okay, you're basically talking about expression prime here, right? Yes, I agree with you. It can be plus,
Plus, minus.
epsilon as well. Epsilon is also considered as a symbol. Okay, like an empty string. Okay, I agree with you. So now, done. Okay, very good. Oh, low battery. You know what? I forgot to plug it in. All right. Thank you. Okay. I think you saved those who left early. Yes. They should really thank you. Okay. How about turn over here? What should be the first set for turn? Okay, let's try. Okay. Actually, turn would be also easy, right? Would you agree? Turn itself must first produce factor. factor must first produce either this or this or this. Wouldn't you agree? The first of term would just be the first of expression prime. Oh, sorry, will be the first of expression. Agree? Okay. Okay, term will be like that. How about term prime? Okay, so now for term prime over here, so now let's use another color here. So now for term prime, right? That's easy. Multiplication, this, pretty much like how we figure out for expression prime, right? So that one is also fine over here. Okay, for factor, that's quite easy, right? Straightforward, just like that. Okay, any questions? We only talk about a bit intuition about what first set really means. Apparently, first set is something that you don't really calculate at the runtime. You can definitely calculate beforehand, before you start processing your grammar. You can imagine that maybe before you start your top-down parsing procedure, you may have a hash table, for example, called the first set. You match from every terminal into their first set, also match from every variable into their first set. That's something what you will do. Okay? Once because grammar doesn't change at the runtime, so you don't have to change it either. Okay, any question about first set? Okay. And now let's look at the formal definition. Okay, actually that's already on this iPad. So there are two cases apparently. So now in the case where the alpha you want to calculate is simply just a terminal, it will just be a singleton set, right? Like a number or the other things, just like a token. But now this one here, I'm just using some set comprehension notation. I'll explain that to you. Okay, you can think about it a little bit more. I'm saying that in case alpha is actually a variable, what should be the first set? Okay, thinking this way. Maybe I can switch the iPad and show it to you. That's this case over here. When alpha is actually a variable, how do we calculate its first set? The first set is going to be all the words. And the words will simply just be no variables, right? Just sigma star. That one's easy to see. And now we want to say alpha itself may take as many derivations as possible into a string. And then we take the first word. So this is the first word. And then it's all such W that will make the set. Okay? Whatever beta is, just whatever follow the first word. So that one is a little bit less critical. Okay? Okay, so that formal definition is not too bad. Okay, just help you read it. Okay, so now let's go back to first set example. We talk about it. Okay, any questions so far? Okay, let me talk about a slight extension. Okay, for the first set. That's the algorithm. I'll do that on Monday. Okay, I gotta trace it together with you. What we just have seen is this particular first set, which means the domain can be either a variable, it can be a token, or it can be epsilon, can be EOF, right? Any symbols or variables, basically. And the range will just be a set of symbols. Okay, that's the first. And then, one thing, I think for this guy here, you don't have to worry about the RHS. We're going to talk about RHS in the algorithm on Monday. But now, we're going to have some extended version or overloaded version of first. Just make it a little bit more useful. Okay? So now notice the difference. Rather than taking a single variable or single token, it's going to be a series of variables and tokens. Well, why would that be useful? Let me show you the example right away. Okay? I'll show you the formal definition in a bit. Let's do this. We still got this grammar here. Okay? Still this grammar. The same as before. But now you can see what we have over here. We want to know what's the first of turn expression prime. You can see, rather than just saying what's the first of turn or what's the first of expression prime, we say what's the first of the right-hand side of some production rule. That's the intuition. Okay? So now I would like to refer you back to this particular thing I just drew previously. Okay? A little bit messy, but let's say this is my current focus of my top-down parsing, and then this is A. Okay, A produces certain thing. It's simply variable and also symbol mix, right? That's a production rule. Rule number 1. And also it could be, or alternatively, V2. Alternatively, V3 over here. Let's say 3 things. So now the way I drew before is to say we look at the first symbol over here, right? So now we extend that definition over here to say, over here we want to calculate what's the first of this particular production rule. Figure that out, okay? It's going to be a set of symbol possibly. And also we're going to figure out what's the first of this particular production rule. And what is the first of this particular production rule. Figure out every one of them. You can definitely calculate by using the algorithm, which we'll see on Monday. Once you have calculated them, you want to see what's the current word I want to match, right? The current word. It may be, for example, X. Okay? So in order for me to decide which one to really do, what should I do? I might want to say if X is a member of, can I just say this, just make it a little bit easier. Can we say this particular set is F1, this particular set is F2, this particular set is F3 that we compute, right? If X is simply a member of F1, of course I have to choose this rule, right? If X is a member of F2, of course I have to choose this rule. If X is a member of F3, and I have to choose this rule, okay? I might know what your question might be, but say it anyway.
What if you have 2 different sets?
Good question. Good question. It's completely legitimate. That's exactly what I'm expecting, right? So now the question was, what if X is a member of F1 and X is a member of F2 is true simultaneously? It's possible, okay? Let's say it's true at the same time. That implies your grammar is not backtrack-free. A backtrack-free grammar should be such that, for example, in this case, F1 intersect with F2, intersect with F3 should be empty, which means they got disjoint sets of symbols for you to choose from. Okay? Good. I think that's a good question. Okay, so I know it's a little bit overwhelming today, I guess. So what should you do in order to survive in quiz number 3, right? Sure. I'll make sure I upload it. Don't worry. I'll make sure. Yeah, that's not a problem. What I would do, I do appreciate that this is a hard subject, right? So I will try to think about some exercise that I'll put it online, maybe for you to think through during the reading week. And then, meanwhile, review the algorithm, especially do me just one favor before Monday, okay? Before Monday, try to review the slides all the way up to here, up to slide 46. Okay, that will help you on Monday. Okay, I'll stop here.